Here we use the Newton's law of cooling equation given by T of T equals Ts plus To minus Ts times e raised to the power of negative kT. This T of T represents the temperature of the object at any time t. Ts is the surrounding temperature and To is the initial temperature of the object. K is the constant that has to be determined and T is time. So let's plug in the information given to determine the value of K first. That is, TO is the initial temperature of the thermometer, which is 9 degrees centigrade, and Ts is the surrounding temperature, which is 33 degrees centigrade. And after 3 minutes, the temperature reaches 33 degrees centigrade. So let's plug in all this information here. So T of T equals 33, and this equals Ts. I'm sorry, this T of T is actually 13 degrees centigrade. So let's change this T of T. That is, after 3 minutes, the temperature of the thermometer reaches 13 degrees centigrade. So we write 13 equals Ts, which is the surrounding temperature, 33, plus T0 is the initial temperature of the thermometer, which reads 9 minus 33, and this is multiplied with the e raised to the power of negative k times t is 3, because after 3 minutes the temperature is 13 degrees centigrade. So let's simplify this and solve for k from this equation. First, I subtract 33 from both sides. So we get 13 minus 33 is negative 20, and this equals 9 minus 33 equals negative 24 times e raised to the power of negative 3k. We divide both sides by negative 1, and this means these two negatives will get cancelled, and we can also divide by 24 on both sides, which gives 20 by 24 equals e raised to the power of negative 3k. Now let's take natural logarithm on both sides, and we will solve for k. So it is natural logarithm of 20 over 24. This equals natural logarithm of e raised to the power of negative 3k. We now bring this exponent, that is negative 3k, to the front by using the power rule of natural logarithm. And so we can write this as equal to negative 3k times natural logarithm of e. The value of natural logarithm of e is 1. So we can remove this from this equation. And so on the left side, we have a natural logarithm of 20 over 24. We have to divide both sides by negative 3 so that we get k. So therefore, k equals natural logarithm of 20 over 24, and this is divided by negative 3. And when we plug this into the calculator and approximate the k, we get it is approximately 0.06077. This is the approximate value of k rounded to 5 decimal places. Okay, now that we have determined the value of k, we can rewrite this temperature equation at time t, that is T of t. This equals Ts is 33, and the To minus Ts, this equals To is the temperature of the thermometer initially, 9 minus Ts is 33, and this is negative 24. So I write negative 24 e raised to the power of negative k times t, that is negative of 0.06077 times t. So this is the temperature equation which we will use to determine these temperatures after 5 minutes as well as after 10 minutes. So first let's plug in t equal to 5 into this equation, that is t of 5. This equals 33 minus 24 times e raised to the power of negative 0.06077 times replace T by 5. We simplify this using the calculator and find the value, and this is approximated to two decimal places. We get 15.29 degree centigrade. So this is the temperature of the thermometer after 5 minutes. Now we will determine the temperature of the thermometer after 10 minutes by plugging in T equal to 10 into this equation. So we get T of 10. This equals 33 minus 24 times e raised to the power of negative of 0.06077 times replace t by 10. So we simplify this expression and plug it into the calculator. And when we do that, we get approximately 19.93 degree centigrade. So this is the temperature of the thermometer after 10 minutes.